let's try to model a rocket launch and see what sort of differential equation we get. So we're going to suppose that we're launching our rocket straight upwards, which is a good direction to send rockets. If the pointy end of the rocket is pointed up, then you might be getting to outer space. So let's suppose that this rocket engine produces T newtons of thrust and it burns lambda kilograms per second of fuel. So the fully fueled mass of the rocket is I'm going to call m sub 0, and the air resistance experienced by the rocket is, let's just suppose that it's some constant times the velocity. This isn't always a great model for air resistance, but it's going to be good enough for us for now. So let's see what we come up with. So the key idea for modeling motion is Newton's second law, which says, right, your sum of all of the forces acting on an object is equal to the rate of change of the mass times the velocity. Now, you're probably more familiar with Newton's second law being F equals ma, but this actually assumes that m is a constant. If you have a situation where the mass of your accelerating object is not constant, then this is what you have to write for Newton's second law. And our mass is changing because the rocket is burning fuel as it goes. And so as it burns fuel, it doesn't have to carry that fuel anymore because it burnt it. And so the mass of the rocket will decrease as it burns through that fuel. Okay, so let's write out all of the forces on this rocket. Maybe just to keep track of things, let's draw a little rocket. So it has this rocket engine on the back and it's spewing mass out the back. And let's see, so there's a thrust that is pushing this upwards. Once it starts moving, there will be air resistance pushing down, and also there's gravity. And the force due to gravity is m times g. So we're going to assume we're near the surface of the Earth where gravity is approximately constant. You have to get pretty far from the surface of the Earth before decreasing gravity has an appreciable effect. Okay, so the forces here are, there's the thrust acting upwards, and then acting downwards we need a minus sign. So there's air resistance, which is constant times velocity. And then there's also gravity acting downwards, which is m times g. Okay, on the right-hand side, we need the derivative of m times v. And remember, both of these are functions of time. M, the mass of our rocket, is not a constant. It starts out at m naught, but as soon as we light that candle, it starts burning fuel and the mass changes. So we have to use the product rule to write down this derivative. So it's rate of change of mass times v plus the mass function times the rate of change of v. Okay, so since there are two things that vary with time here, there's the velocity and the mass, it seems like we might have two unknown equations. But actually, we can write down what the mass function is explicitly. So we know that the mass of the rocket is initially m sub 0, and then it's burning fuel at a rate of lambda kilograms per second. So we need to subtract off, after t seconds, we need to subtract off the mass of the fuel burnt, and that's lambda times t. Okay, so the function m is actually, it's not an unknown function of t, it's a function of t that we can write. And for the record, right, we can compute this derivative of this, dm dt, looks like it's just minus lambda. Okay, so putting this into our differential equation here, we get the thrust, which we're going to take as constant, minus kv, and k is constant, minus m, which is m naught minus lambda t times g, equals dm dt is minus lambda times v plus m times dv dt. Okay, so this is the differential equation we get. Now, if you keep your eye on things here, we have two terms with v and we have a term with the derivative of v. So it looks like this is going to be a linear differential equation. Let's just rearrange things so that it looks like how we're used to. So let's move all the terms without a v to the left. So we have thrust minus m sub 0 minus lambda t times g equals, and then on the other side we'll have our terms with v's. So our derivative term is m times dv dt. Oh, and I guess for m I should put in our mass function, which is m naught minus lambda t times dv dt. Then we need to move this kv term over, so plus kv, but then there's a minus lambda v. Okay, so altogether we have capital T minus m sub 0 minus lambda t times g equals m sub 0 minus lambda t times dv dt plus, and then we should factor out that v, so k minus lambda times v. All right, so now this is a linear differential equation. We could solve this as a linear differential equation to get a model of what the velocity of this rocket as a what this velocity is as a function of time. And then if we add some initial conditions, like say the initial height of the rocket is 0 because it's starting on the ground, and the initial velocity of the rocket is also 0 because the rocket starts at rest on the launch pad, we could actually solve this differential equation to find v, and then integrate one more time to find the height as a function of time. So we could use this differential equation to get some sort of idea of how high our rocket is going to go. So this is good, generally a pretty good result, but of course actual rocket launches are a little more complicated. The way we've written this equation, the rocket starts out traveling straight up and keeps traveling straight up, but most rockets don't do that. If you want to get to orbit, you actually have to turn sideways so that you go around the planet instead of straight away from the planet. Also, if you do go high enough, eventually gravity starts changing on you because you're getting further from the Earth. And also, air resistance, the air resistance is going to change as you go high enough because the atmosphere gets less and less dense. So this is sort of a decent first try at modeling a rocket launch, but it's not going to get you all the way to space. But it is linear, so at least you can solve it in principle.